Hi, everybody. Hope you're doing well. This is the first video in a series of videos that will come out this week for you to review the mole, and then we're going to learn some new stuff about molarity and stoichiometry. So let's get started. If you remember, last semester we learned all about the mole. We sang a great song. I'm not going to sing it for you right now because I am very tone deaf. But you guys remember that the mole is a counting unit. Remember that a counting unit is something that stands for a number. So just like a dozen means 12, a mole has a number associated with it as well. And that number is Avogadro's number, 6.02 times 10 to the 23rd. So this is the number of atoms or molecules or formula units that are in any one mole of something. And last semester, we learned how to convert between units using Avogadro's number. I have a couple of examples here for you, but hopefully you've seen the review video that I posted on Classroom already. Maybe you've even attempted the mole conversion worksheets as part of your review. And if you've done that already, then awesome. This will be pretty straightforward for you. You can probably skip forward a couple of minutes because I'm just going to do some of these review in case you haven't watched that video or in case you haven't tried those review worksheets yet. So let's start with number one. It says, how many molecules are in 2.5 moles of water? So we always start with what we're given. So in this example, we are given 2.5 moles of water. We write that as 2.5 moles of water, H2O, and we are going to convert to molecules. So I'm going to write that on the right-hand side of my screen. Now, how do I get from moles to molecules? Well, we know that if I want to cancel out of the unit of moles, I have to write that on the bottom. It only cancels if I write moles on the bottom. Then I write the unit that I'm going to on the top, which would be molecules. There is no abbreviation for molecules. You have to write molecules out completely. Okay. Then I just need to fill in my conversion factor. Now, that's what this is up here. This is my conversion factor. So for every 1 mole I have 6.02 times 10 to the 23rd molecules. Now, if you're following along at home and you're doing this work in a notebook, then I highly recommend that you go ahead and grab out a scientific calculator or maybe open up a scientific calculator in another web browser, if possible. Otherwise, I'm going to show you the answer, so it's not a big deal. So to solve this problem, we multiply across the top and then divide by what's on the bottom. So I'm going to take 2.5, multiply it by 6.02 times 10 to the 23rd. I'm going to get an answer, and I'm going to divide that answer by 1. Luckily for us, dividing by 1 gives us the same number. So when we get our answer, it's going to be 1.505 times 10 to the 24th molecules. Now I would need to round this to sig figs, so my final answer will be 1.5 times 10 to the 24th molecules. All right, let's do another example, this time going the opposite direction. So now what I want to know is how many moles there are if I have 1.42 times 10 to the 24th atoms. So again, you start with a given piece of information. 42 times 10 to the 24th atoms of iron. Then on the right-hand side, we write moles of iron because we know that's where we're going. And then we just set up our conversion. The unit that goes on the bottom is the unit that we want to cancel out of, which in this case is atoms. And the unit that we're going to goes on the top, which in this case is moles. Now, our conversion factor is the same conversion factor that we used in the last problem. However, we now have moles on the top and atoms on the bottom, which is the opposite of what we had before. we need to make sure that we keep this conversion factor the same. For every 1 mole, there are 6.02 times 10 to the 23rd atoms. So that number, that Avogadro's number, can be on the top of the conversion factor or on the bottom. It really depends on where the units are. But Avogadro's number, 6.02 times 10 to the 23rd, needs to stay with the atoms, the molecules, the formula units, whatever you have. And now we solve. So I'm going to take that 1.42 times 10 to the 24th, multiply by 1. So I get 1.42 times 10 to the 24th atoms. And then I divide that by 6.02 times 10 to the 23rd atoms. When I divide that out, I get 2.358 moles of iron. I need to think about sig figs. My answer is going to be 2.36 because that 8 rounds the 5 up. My final answer is 2.36 moles of iron. Now, that's just a brief little review using atoms, molecules, whatever, converting directly to moles. But that's not the only thing we learned how to do last semester. Last semester, we also learned about how much a mole weighs. Now, we know that the mole is a counting unit and not a mass unit. And if you remember, we did a little show and tell showing you that I could have a mole of a bunch of different substances, and those moles would all be different sizes and masses because it depends on what that substance is made of. Right? So if I have if I have carbon, well, the molar mass of carbon, that is the mass of 1 mole, is 12.01 grams, and you can find that on the periodic table. If you don't have your periodic table out, I would find one. Pause the video, find a periodic table because we will be using it for the rest of this video. So like I said, the mass of 1 mole of carbon is 12.01 grams. So if I have 1 mole of carbon and I set it on a scale, it would weigh 12.01 grams or 12.01 G/mol. That means that for every 12.01 grams, we have 1 mole. This is our conversion factor rate. But what if I have a compound? In a compound, we would add up the element pieces to find the mass of the whole compound. So, for example, carbon dioxide. In carbon dioxide, I have 1 atom of carbon, but I also have 2 atoms of oxygen. So I need to add those masses together from the periodic table, so 12.01 grams per mole, plus 2 oxygen atoms, right? So 2 times 16. I add those together and I get a total molar mass of 44.01. This is the molar mass of the whole compound. And once we learned how to do this, it opened us up for more calculations. So let's do one. 7 moles of H2O. So the units that go on the bottom, that's moles of water. And on the top, I'm going to have grams of water. The problem is, what is this conversion factor? What numbers go here? Since we have grams and moles in our conversion factor, that's the key that we need to be looking for molar mass, right? So molar mass has that grams and moles together. So I need to add up these component pieces of water, so 2 hydrogens and 1 oxygen. I need to add those up and figure out what my overall molar mass is. The molar mass of 1 hydrogen is 1.01, but I have 2 of them. And then the molar mass of oxygen is 16, and I just have 1 of them. So if you add those up, you get 18.01 grams per mole. Now I need to take that number and put it into my conversion factor. The 18.01 stays with the grams. So 18.01 grams, and that's how much 1 mole of water weighs. Anytime 100% of the time when you use molar mass as a conversion factor, there will always be a 1 next to the moles. Every time, no thinking, put a 1 next to the moles if you're using molar mass. Then to solve, we just multiply across the top and divide by what's on the bottom. So 10.4. I already rounded it to sig figs for you. So 10.4 grams of water. Now in this example, I have 24 grams of NH3, and I want to solve for moles this time of NH3. But when I set up my conversion factor, grams is going to end up on the bottom. In the last problem, grams was on the top. So we have to figure out how that's going to affect our math here once we put in our conversion factor. It does not matter if that grams is on the bottom or if grams was on the top. It's, it can be switched around. It's a ratio. So we still have grams and moles together, which means we still need the molar mass. Well, the mass of 1 nitrogen is 14.01. The mass of 1 hydrogen is 1.01, but I have 3 of them, and that's the molar mass, grams per mole, for ammonia, NH3. Again, this 17.04 goes with the grams, 17.04, and that's for every 1 mole. Then all I have to do, 24 divided by 17.04. So then with sig figs, you get 1.4 moles of NH3 as your final answer. Let's go a step further. What if I have 24 grams of NH3, just like I did in the last problem, but now I want to know how many atoms there are. All right, so I've got that 1.4 moles of NH3 that I found in the previous problem. So I have moles on the left, and I know that I want to convert to atoms of NH3. So I can set up my conversion factor. Moles goes on the bottom. Atoms goes on the top. And I am going to plug in Avogadro's number as my conversion factor because I know that for every 1 mole, there are 6.02 times 10 to the 23 atoms. And including sig figs, I end up with 8.4 times 10 to the 23rd atoms of ammonia. Now, you could hypothetically string all this together if you wanted to. Convert grams to moles, so grams and moles. Then you could go from moles to atoms, right? And that would be a 2-step conversion process. You would still end up with what you wanted, the atoms of NH3, but we got the same thing when we did it in 2 individual steps versus when we did it in 1 long chain. So I would prefer if you did 1 long chain, but if you want to do 2 steps, that's totally fine. Now, that's basically everything we learned last semester. But what I didn't give you last semester was, wait for it, a top 10 handout covering mole conversions. But you have it now. It has been posted on Google Classroom for you to print or look at. If you do not have a printer at home, what I suggest is pulling it up on Google Classroom and taking screenshots of both pages. There's a front side and a back side. We're not going to use the back side today, but we are going to use the front side, and you are going to want to be able to refer back to this mole map. So I highly suggest either printing this top 10 handout or saving screenshots on your phone. So what we've done today so far is just review how to do moles to grams, right? And how to do moles to particles, atoms, molecules, whatever. We are going to save the molarity thing for later. That's the next video. And what we're going to do right now is talk about this wing. Okay? So basically with this mole map here, it's just showing you how to get from one thing to the other. So if you want to get from number of grams to number of moles, you use the molar mass, right? If you want to get from number of moles to number of particles, you use Avogadro's number. So there's a new conversion that we haven't learned yet that uses moles and liters of a gas. So let's learn a little bit more about that. Our bud, Amedeo Avogadro, right? The guy who created Avogadro's number, 6.02 times 10 to the 23rd. He proposed another hypothesis in his research. He said that if you have two gases that have identical volumes, then they should have the same number of particles in those volumes. And he argued his case. He was like, since the total volume that a gas occupies is made up of mostly empty space, right? Picture a balloon. How much space is just, empty and how much is filled of air particles? Right? The particles are so small that the empty space totally drowns out the size of the particles. So essentially, the size of the particles is negligible, meaning it doesn't matter at all. And therefore, if you have the same number of particles in equal volumes, then you would have the same number of moles in equal volumes. And so he set up this equality. He said that 1 mole of any gas will always have the same volume. And he said that volume was 22.4 liters. So essentially what he was saying is gas particles are so tiny that they're so far apart that it doesn't really matter how many particles you have in there. 1 mole is going to be the same size because you can just squish these particles a little bit closer together and they'll take up the same amount of space. So same number of particles, right? Same number of moles, same volume. That's what he argued. Unfortunately, this hypothesis only holds true at standard temperature and pressure, which sometimes I will be abbreviating as STP. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Hopefully you remember those units when we talked about units at the very beginning of the year in August. But this is like a standard temperature that all gases behave pretty similarly. Once you start to change the temperature and pressure, then gases sort of freak out. Hopefully we're going to get to talk about gases towards the end of this year, and we'll get more into that at that time. But for now, you just need to know that at standard temperature and pressure, 1 mole of any gas will take up 22.4 liters of space. That's the bottom line. What you need to know is this equality. And we can use that hypothesis, that equality, to convert between moles of a gas and liters of a gas. For example, if I have 2.5 moles of H2, and I want to know how many liters of H2 I have, I can set up a little conversion. I'm going to put moles on the bottom, liters on the top, and then I just fill in that conversion factor, right? That 22, so that 22.4 there, that's how many liters there are in 1 mole. So when I put this in my conversion factor, again, I just have 1 mole, but I have 22.4 liters. Then to solve, you just do your normal multiplication, 2.5 times 22.4, and we get 56 liters of H2. Now, I will say it's very, very, very important that you realize that this equality only works for gases. If you do not have a gas, this hypothesis does not work. It's the fact that we have gases and that we can, sort of squish the volume of gases, we can squish the particles closer together because there's so much empty space. That's the only reason that this hypothesis works. If you don't have a gas, then you cannot use this equality. Okay, let's do another example. Now it says at STP, remember STP stands for standard temperature and pressure. I have 7.11 moles of H2O4. And I want to can convert that to liters of N2O4. So when I set up my conversion, moles goes on the bottom, liters goes on the top, and then I need to plug in my conversion factor. Now, in this example, liters is on the top again, so I've got the 22.4 that goes with the liters, and that's over 1 mole. So to solve, again, I'm just multiplying liters of N2O4. What if, starting with liters, now I've got 8.2 liters of O2. Now I want to know how many moles of O2 that is. Okay, well, again, I can set up my conversion. This time, liters of O2 is going to go on the bottom, while moles of O2 goes on the top. But it doesn't matter, remember, because I have a conversion factor. Conversion factor doesn't matter which way is up, which is down. You just have to keep the number with units. So that 22.4 has to stay with the liters. There are 22.4 liters of a gas in every 1 mole. So this is not a multiplication problem, it's a division problem. 18.2 divided by 22.4, that gives me, with sig figs, 0.813 moles of oxygen gas. Last one, and with sig figs you get 1.79 moles of NH3. So now let's take all of this stuff about gases and mix it up with what we already know about particles and molar mass. Let's do some mixed multi-step problems here. When I've got multi-step problems and when I've got all sorts of things mixed up together, this mole map is going to become super useful because you can use it to plan out how you're going to get where you want to get. So in this first example, it says how much space, when it says space, we should volume, okay? How much space would 3.44 times 10 to the 24th molecules take up at STP? So I'm starting in molecules. So I'm starting on the top right in molecules. If I'm in molecules or particles, there's only one place I can go. I can only go to moles. But once I'm in moles, I can go to volume, right? And I know that I can go this way because N2 is a gas, right? So I'm going to go from particles or molecules in my case to moles, then from moles to liters. That's my plan. So when I go to set up this conversion, 3.44 times 10 to the 24 molecules. And the first thing I'm going to do is convert that molecules to moles. So when I set up that conversion, molecules is going to go on the bottom, moles is going to go on the top, okay? But I don't need to plug in any conversion factors yet. Hold on that for right now. Because I still have one more step. From moles, and I know that the molecules are going to cancel out because they're on opposite sides. Now I need to get the moles to cancel out. So moles is going to be on the bottom, and liters is going to be on the top. So I should end up, because the moles are going to cancel out, I should end up in liters. Now, when I add in those conversion factors, let's look at our mole map. To get from number of particles to number of moles, I need to use Avogadro's number, 6.02 times 10 to the 23rd. And there's that many molecules in 1 mole. So now I'm in moles. Right? To get from moles to liters, I need to use this new Avogadro equality that says there are 22.4 liters in any 1 mole. So when I multiply across the top, I take my 3.44 times 10 to the 24th, multiply that times 1 times 22.4, so essentially just times 22.4, and you get a number. That number is 7.7056 times 10 to the 25th. then you're going to take that number and divide that number by 6.02 times 10 to the 23rd, which will give you your final answer, 128 liters of N2. So that's a multi-step example. I do, of course, have more examples that we're going to look at. Let's do some more. And this is why I said you're going to want to have your mole map on your phone or print it out in front of you, because we're going to keep referring back to this. In this new example, I have 690 grams of carbon dioxide. Carbon dioxide is a gas, and I am going to find volume of that gas at STP. Then I'm also going to find how many molecules that is. So, there's a lot going on in this problem, but let's figure out a path first. Let's first go from grams to volume, because that's the first question. So to go from grams to volume, this is where I'm going to start. I'm going to start in number of grams. So I'm going to go from grams, and I need to get to volume. So this is where I need to end up. To get there, I have to go through moles. Okay? I'm going to start in grams, I'm going to go to moles, then I'm going to go to liters. But the question also asks how many molecules is that? Unfortunately, I cannot go from liters to molecules. That doesn't work. So I'm going to have to go from grams to moles, and then from moles to particles. So I sort of have two steps. I have like a diverging, you can go here, and then I have a fork in the road. I'm going to go both ways. So let's get started on that math. Let's do the top one first. Moles and grams, right? That's molar mass. If you look at this is where we're looking right here. To get from grams to moles, we have to use the molar mass, which means we have to calculate the molar mass. Okay, molar mass of carbon dioxide. Carbon is 12.01. Oxygen is 16, but there's two of them. So 16 times 2 is 32 plus 12.01. That's 44.01 grams of carbon dioxide per mole. So when I include that in my factor, 44.1 goes on the bottom, 1 goes next to moles. Then in my next conversion factor, I have liters in moles. That's Avogadro's other hypothesis, which says 22.4 liters in every 1 mole. So I can go ahead and calculate this out. I'm going to multiply 690 times 22.4. Take that number, divide it by 44.01, and you'll end up with 350 with sig figs, 350 liters of carbon dioxide, which again is a lot of carbon dioxide. So that's the first step. We figured out the volume. Second question, that's how many molecules. Well, I already figured out the molar mass. I can plug that in. Okay, so I've got the first conversion filled in. Then the second conversion is Avogadro's number, 6.02 times 10 to the 23rd molecules in 1 mole. So again, multiply across the top, 690 times 6.02 times 10 to the 23rd. Take that number, divide it by 44.01, and you end up using correct statistics with 9.4 times 10 to the 24th molecules. So we've solved it. Remember, at any time you can pause the video, rewind, watch a section again. I'm going to go on to one last example problem here. This time I want to know how many formula units are in 25.5 grams of magnesium bromide. So let's figure out what we're doing here. I'm trying to figure out how many formula units are in 25.5 grams of magnesium bromide. So I'm in grams. I need to go to formula units. If you're looking at your mole map, we have to go from grams first to moles, and then we can go from moles to formula units. Okay, I don't mean to insult you, I'm just abbreviating formula units, okay? So let's take a chill pill. So let's set this up. 25 grams of magnesium bromide. If you don't understand how I got MgBr2, you need to go back and refresh your ionic nomenclature skeleton here. Grams of MgBr2 goes on the bottom, moles goes on the top, then my grams will cancel out, I'll be in moles, then I can go from moles. Again, that moles will be on the bottom so that it cancels out. And then on the top, the unit that I'm going to is FUs, or formula units. Then I just need to fill in my conversion structure. Oh no, moles and grams. I'm gonna have to figure out my molar mass. The molar mass of magnesium is 24.31. And the molar mass of bromine is 79.90. Oh, those all look like 9s. There you go. 79.90, and there's 2 of them. Okay, so overall, the molar mass of magnesium bromide is 184.11. That goes to 4.11. How many grams are in 1 mole? Well, the factor is a little bit easier because it's just Avogadro's number. There are 6.02 times 10 to the 23rd formula units in 1 mole. Whoa, I can change the color of this thing. Okay, that's beside the point. Now, I need to solve. So I multiply across the top, take that number, divide it by the molar mass that we found, 184.11, and you get 8.34 times 10 to the 22nd. What's a 2? 22nd formula units of magnesium bromide. So basically, what have we covered in this video? We have covered essentially all of these conversions here. We reviewed Avogadro's number, we reviewed molar mass, and then we learned something new, the molar volume of gases, so that 22.4. We've done 3 out of the 4 things on this mole map, so the next video is going to be about molarity. Take a break, come back, maybe give your brain a little break, or maybe go back and review some of those problems that you don't know how to do. Might be a good use of your time. Anyway, I'll see you next time in the molarity video.